So here it somewhat looks like this. So these are the allowed bands and these are the gaps between the bands. Okay. The lowermost bands are almost completely filled by electrons in the solid, while the uppermost band are entirely empty. Okay, so the lowermost bands are almost entirely filled by your ground state electrons. Okay, while the uppermost bands are almost entirely empty. Okay, so this is the structure. However, the interesting aspect comes in the transition between filled bands and empty bands. Okay, so here we can define several types of bands. So we can define something called the valence band. This is the highest band that is filled with electrons at 0 Kelvin. So for our case, this is our valence band. Okay. Then you have, after this, the conduction band. The next band above the valence band at 0 Kelvin. Okay, so this is our conduction band. This band is entirely filled with electrons. The band above this is called the conduction band. Now this may or may not be filled with electrons at 0 Kelvin. We will discuss different cases and see how the conduction band looks like for different types of materials. And we also have this energy spacing between the conduction band and the valence band is called the band gap. Okay, so band gap is the region of forbidden energy between the valence and the conduction bands, where no electrons can reside. Okay. Now we will discuss two interesting facts. Electrical conductors. So the materials, the solid materials can be separated into conductors, insulators and semiconductors. We will see what the difference between them are. Electrical conductors. So these are solids for which the valence and conduction bands overlap and there is no band gap. Okay, so this is a case where this is your conduction band and this is your valence band. As you can see, these two bands are overlapping and the band gap between them is 0. Okay. Now valence band is completely filled with electrons and conduction band has no electrons typically. But here, because they are overlapping in energy levels, part of the electrons in the valence band can easily move into the conduction band and partially fill it. Okay. Hence, conduction band is partially filled with electrons even at 0 kelvins. So why does this help in electrical conductivity? Okay. So let's look at this point then, that electrical conduction in a solid can only occur through electrons or holes. We will discuss holes later. I am putting this terminology out here, that occupy partially filled conduction band or valence band. So electrons that occupy partially filled conduction band or holes that occupy partially filled valence band. Those are the two types of charge carriers that can conduct electricity in a solid. Electrons that are there in the conduction band and holes which are basically empty spaces where electrons should be in, that are there in the valence band. Okay. In such cases, there are sufficient empty, closely spaced energy levels in the band for the electrons or holes to move to as it gains energy when an electrical voltage potential is applied across the solid. So the idea is, look at your conduction band for a conductor. Because it is overlapping with your valence band, part of the conduction band is filled with electrons and part of it is empty, but this empty spaces are very closely spaced. So an electron here can easily move to one of the empty spots here when it gets some excess energy from the electrical voltage potential that is being applied across the solid. Okay. Similarly, In the conduction band, for such a case, this is your conduction band. These electrons here has been transferred to the valence band. So there is some empty spaces in the conduction band. And these are like empty holes here. Okay. And the electrons here can now move here and the holes can move downwards. Okay. And with a small increment of energy that these holes are gain because of the electrical voltage potential that is applied here. So basically these holes can move down here and the electrons can move up here. Okay. So this way, thus conduction band electrons can easily and valence band holes can easily accept energy from an applied So the valence band holes and the conduction band electrons can easily accept energy from an applied electrical field and get elevated to a nearby empty energy level. Okay. To become free charge carriers. Okay. These are often called free electrons. Remember that holes are basically imaginary spaces, right? It is the electrons here that are being promoted here and the holes are therefore going down. Okay. So the flow of holes in the conduction band in the valence band is similar to the flow of electrons in the conduction band. And once these electrons get elevated from here to here or here to here, they become free electrons which are very loosely tied to the atoms and hence can flow with the potential gradient that has been applied across that substance. Similarly, the holes here, once they go into this empty space, into this electron area, there are plenty of electrons that can move to these holes and the holes can transport very easily from one atom to the other. Okay. Remember, what is happening here is that the electrons are jumping from one atom to the other atom because of the applied potential gradient, and it can do that because there is very little energy gradients in these partially filled levels. Okay. So these free charge carriers can move from one atom to another atom in the solid and hence flow across the solid, creating an electrical current across the applied potential gradient. Okay. So this is what happens in a conductor, that electrons and holes get promoted to nearby closely spaced energy levels and hence hop from one atom to other and create a flow of charges due to the applied potential gradient, and hence you can see a current forming very quickly when you put a potential gradient across a conductor. And all of this happens because your conduction band and valence band are overlapping. Okay. So then what is an insulator? So let us discuss an insulator next. Insulators are solids for which the band gap between the valence and conduction band is greater than 4 electron volts. Okay, so here this is your valence band and this is your conduction band. Sorry, this is your valence band which is completely filled with electrons, and this is your conduction band. They are very far apart and the distance between these E gap is greater than 4 electron volts, which is a large energy gap in respect to for atoms. Okay, so in this case, even at higher temperatures, and with even high potential gradients, there just isn't enough energy for any electron to move across this large energy jump and go to the conduction band. So even at high temperatures, there is very few electrons that can actually be found in the conduction band. Unlike in the conductor, where even at 0 kelvins, you have a lot of electrons in the conduction band. Okay. So as a result, since there are no electrons and correspondingly no holes here, there isn't any closely spaced available energy level to which electrons can go to. Okay, all the levels are filled here and all this empty space is filled with holes here. So there is no empty space for holes to move into, no empty space for electrons to move into, which is not very far away in terms of energy. So there is no way for the electrons to move or jump. And as a result, even if you give a large potential gradient, you do not see a current flow being generated across it. And this is what we call insulators have high resistivity. Okay. Then what about semiconductors? So here, these are solids for which the band gap is between 0 to 4 eV. So here, the valence bands and conduction bands do not overlap, but they are close to each other. Okay, so this is your valence band and this is your conduction band. Conduction band and this is your valence band. And here, E gap is less than 4 electron volts. And hence, what happens is, at 0 kelvins, there are no electrons in the conduction band. However, as the temperature rises, the thermal energy available to the electrons make it possible for some of the electrons to have enough energy to move into your conduction band. So you will have some electrons in the conduction band and some holes in the valence band, especially at reasonably high temperatures. So these semiconductors can conduct electricity to some extent, especially at high temperatures. Okay. So at high temperatures, some electrons have enough energy to jump to the empty conduction band, and hence conduct electricity. So semiconductors are partially conducting at high temperatures. Okay. And we can actually separate out the conductors, insulators and semiconductors by their conductivity. Okay. So the conductivity values for conductors like metals is around 10 to the power 8 ohm inverse meter inverse. Okay. For semiconductors, for example, silicon, germanium, etc., the conductivity value varies from 10 to the power 5 to 10 to the power minus 6 ohm inverse meter inverse. A large range, but still even the highest range is 1000 times less and the lowest range is like 10 to the power 14 times less than a metal conductor. Okay. Whereas insulators, these are ceramics, metal oxides. Here their conductivity is 10 to the power minus 14 ohm inverse meter inverse. So you can see again there is a huge jump from the conductivity of semiconductors to the conductivity of insulators, around 10 to the power 8 times. So even though the conductivity of semiconductors are quite low than conductors, still they are significantly higher than the insulators. Okay. So you can actually distinguish these three types of materials fairly easily by measuring their conductivity. Okay. So I will stop today at this point. We will continue our discussion on solar PV technologies in the next class. Thank you for listening and we will meet you in the next class again. Thank you.